Hello and welcome to our next Shell Eco Marathon virtual learning session with Altair Engineering. And welcome back to those of you who have already joined one of our previous sessions. My name is still Norman Koch and I'm the Global General Manager of Shell Eco Marathon. I want to start off by thanking all of you for your flexibility and understanding as we developed the Shell Eco Marathon due to the impact of COVID-19. As the situation continues to change, the safety and health of our Shell Eco Marathon participants and our organizing teams remains our top priority. Given the current status, we're excited to have you all with us in this new digital environment to kick off our virtual learning sessions, all from the safety of your homes. Today, you will be hearing from Paul Over from Altair Engineering about lower energy consumption and better performance with optimized aerodynamics. Altair, as you know, is a global technology company that provides software and cloud solutions in product development, high-performance computing, and data analytics. Altair has been supporting Shell Eco Marathon by supplying licenses, training, and support for Altair HyperWorks to the participating students in Shell Eco Marathon. Paul is a master's student of theoretical mechanical engineering at the Hamburg Technology University. His focus is on fluid mechanics and aeroacoustics. He led some of the CFD activities for thermal management and race aerodynamics at the Formula student team Ignition in Hamburg. After an internship at Altair in Sweden to create the Ultra Fluid X ebook, he continues to work as student ambassador for Altair. In his free time, believe it or not, he loves fluids too. He is free diving, fishing, and enjoys all sorts of water sports. Welcome to the show, Paul, and we look forward to hearing from you in a few moments. But before we get there, just a couple of housekeeping comments. We would like to make this session as interactive as possible. So if you have any questions, please go to the website menti.com and enter the code shown on the bottom of your screen. On Menti, you will be able to post your questions, but also see other questions that have already been asked and give them a thumbs up so they can rise to the top of the queue. If by any chance you have any issues accessing Menti, you can also post your questions on the YouTube comment box once you're logged into YouTube. And then please ask any question you have and give Paul a really tough time. You can ask him anything you like to related to his presentation on aerodynamics. He will be answering your questions after the presentation part of the session. As you know, this is a live video stream, so if for any reason we run into any technical difficulty, please be patient with us and bear with us while we try to fix the problem. That's pretty much all from me at this point in time. I now have the pleasure to hand over to Paul and introduce the session. Paul, over to you.
Well, thanks, Norman, for the introduction. Welcome to this webinar, guys. Maybe it's not really the Eco Marathon we all wanted to have, but now let's take this time and go further in development. At this place, maybe a big thank to Shell to organize this webinars and put in place this awesome platform. Last days, you had already the opportunity to have a look into analysis and topology optimization with Altair Spire, presented by my colleague Eric. And today, we're going to dive into modern CFD and especially into lower energy consumption and better performance with optimized aerodynamics. So let's hit it. Of course, motorsport is a big engineering thing and motorsport of challenges. Not only automotive companies are continuously under pressure to set new lap time records, develop new technologies, and to keep on breaking their records. Part of this are race cars. They are characterized by highly developed assemblies, engine, chassis, and of course, external aerodynamic and internal aerodynamic characteristics are main part of it. The same yields for the Shell Eco Marathon. Every year, all these teams compete on events in ultra efficiency classes. Beside the drivetrain, the kinematics, and the software, the external aerodynamic is an essential element to reach ultra efficiency. Let's start from the beginning. What really is external automotive aerodynamic? So let's say external automotive aerodynamic is related to the flow around the vehicle. And the flow around the vehicle then directly leads to forces acting on this vehicle. In the picture on the right, you see the lift and the drag force schematically sketched into this graphic. Beside those two forces, there are also lateral forces and moments which are maybe introduced by crosswinds or unsteady road behavior. But the greatest interest will be more in this lift and drag. So what is it? The drag is the force which acts against vehicle direction. It's directly related to fuel consumption, maximum velocity, and range. The lift force is the force which pushes the vehicle on the ground, and it's related to driving stability and cornering behavior. Okay, but how to compare these forces when we look at some cases. There are two equations down on the left side of the page. These equations formulate coefficients. These coefficients belong to the forces, and the best thing about them, they are dimensionless. So we call them coefficient of drag and coefficient of lift. These are two good ways to compare one setup with another without caring about the size of the vehicle's proportions. But now, come back to the forces. To be ultra efficient, the drag should be therefore considered separately, because it is the main part where we come to fuel consumption and maximum velocity and range. So the big question is, where does it originate from? Can those regions really be identified? And can we maybe have a little bit deeper look into it? I just pointed out some sensitive regions on here. And of course, these regions are in general and not more an average kind of thing. So 40% of the overall drag probably comes from the proportion and the shape of the vehicle. 30% from the wheelhouse and the wheel, how it's placed. 10% internal flow and 20% underbody flow. In respect to Shell Eco Marathon vehicles, I think the most important might be the proportion and shape, and of course the wheels and the wheel housing. But why do I talk all the time about external aerodynamics? Yeah, that's a big question. On the left here, you see these characteristics of external aerodynamic characteristics. On the left, on the right, you see a table which shows just some numbers. The EUDC and NEDC just stands for emission test cycles made by the automotive industry. But let's have a look. So imagine you're driving in the city, and now you change that coefficient of drag around 0.01. Then the fuel consumption changes also, and it changes about 0.01 liter per 100 kilometers. That would be related to a change in vehicle mass about 6 kilograms. Now imagine you drive a little bit faster, let's say 120 kilometers an hour. Now we change this coefficient of drag about the same amount. The fuel consumption changes now about 0.09 liters per 100 kilometers. And this is already related to an equivalent mass of 129 kilograms. Quite a lot, don't you think? Okay, so now we got all in place. Let's have a look what it's all about to optimize the aerodynamics. Optimizing these aerodynamics are quite a difficult task. It requires theoretical knowledge, experience, experimental data, maybe from wind tunnel or simulations, and all this put together is used or has to be achieved to reach an efficient, balanced, and good aerodynamic setup. So today my mission is to give you an ultimate insight into lower energy consumption and better performance from optimized aerodynamics. So let's have a look what we're dealing about in detail. This is me, Paul Over, and I'm going to present to you today the optimizing the aerodynamics of the vehicle. And first of all, we have a small look into theory. It's quite a difficult task I had to understand the aerodynamic behavior. So we like to get up some theoretical knowledge from maybe your classes or the school to really follow everything. Of course, simulations are also nowadays an integral part of vehicle development and thus an integral part of engineering's life. So we divide after that theoretical part, there follows a practical one. I'm going to show you some brilliant software which makes it really intuitive to set up a simulation for your own EcoShare marathon racer. And in the end, we, of course, have a look at some results I prepared and talk about common ways to process your simulations in an efficient way and really to get your design iteration going on. And after this whole hour, after this session, you should be able to start with your own ultra-fast simulation. So let's hit it off. Let's start with some basic advices in ground vehicle aerodynamics. How does the reality look like? Okay, it's not really the reality. It's more a kind of a schematic car sketch I took here, but let's try to understand it. First of all, when we imagine we're driving on the road, the air isn't totally stationary in totally equilibrium. The car moves towards the air and the air flows around that car. On the front bumper, the air hits the car directly normal to its surface. The velocity of the air goes to zero and the pressure increases to its local maximum. The air above the front bumper gets pushed up. The velocity rises and the pressure decreases. The effect of suction appears. The same yields for beneath the car. The air gets pressed through the small gap between the car and the road. The effect of suction appears as well. Behind the car, there is a different phenomenon. It's flow separation, which introduces a lot of drag. But now we just only named this only thing which introduced drag. Let's have a look how the reality looks like and which parts also introduce way more drag. Here I took one of your nice cars and just made a sketch on how to look and point out the region which are really sensitive. The percentages which are drawn on the side, they are concluded on the overall drag by just having an optimized or an unoptimized design. For example, the radius at the front bumper, it's causing up to 2% of the drag. The roof contour, here shown at number 5, has an influence about 1%. And to call maybe the lowest installation drag part is the diffuser. It really shows no drag at all. And when you remember the numbers from the beginning, how much energy you could save by optimizing it. Oh, quite a lot, don't you think? So how to optimize it? How to save these amounts? Okay, like I already said, like you saw on the last slide, there were a lot of numbers placed on the lower end of the car. So close to the underbody. The underbody should be separated in ground clearance and pitch and also in underbody covers. If we start now to increase the pitch so the nose of the car goes up, it would lead to increased drag and lift. A negative pitch, so nose down, creates a pseudo diffuser effect on the entire underbody, which reduces the drag and lift. The smaller the ground clearance, the lower the drag, of course. Regarding the lift, there's an optimal ride height for the car. So there's an optimal gap to create the optimum amount of lift. It's a good screw to really get the balance of the aerodynamic setup right. When we come to underbody covers, it's quite important that the flow under the vehicle is smooth. Therefore, we need to reduce the roughness of all the tubes and parts which are down there. So when it's possible to cover the underbody starting from the front as far downstream as possible, that's quite good. But attention here, complex shielding of the underbody is not always possible. Maybe there are thermal requirements, cooling of air transport, or other constraints due to chassis or axles. Like here in the picture, there are only the blue parts were replaced and fully covered. Like I already introduced, there's a design or there's a device which can help quite a lot. It's called the rear diffuser. The installation deck we already had is nearly close to zero, which makes the diffuser really helpful. A well-designed diffuser can help to reduce drag and also lift. In general, longer diffusers are a little bit more efficient, but they only work well for undistributed airflows as found on many of your vehicles. Like here in these small pictures on the right, there we have some special numbers coming up and maybe some strategies to improve their working. Work with these theories and get them to your car and simulate them. Another part on these EcoShell Marathon vehicles are, of course, the wheels. When we're speaking about EcoShell Marathon and taking a look to the picture and also to efficiency, we always see that the wheels are take a big proportion of the overall vehicle. The superposition of the flow around the car and around the wheels leads to a super complex flow. And the additional wheel rotation introduces another additional effect. So that we can sum up the total drag of the car is produced by 30% by how the wheels look like and how the wheels are performed. So there's lots of potential for optimization. So where to attack? We could either alternate the tire, the rim size. We can go to a closed wheel setup instead of an open wheel one. I just want to point out, do experiments or better run simulation to get the optimal. But as well as the wheels, there's also maybe a big last point I'd like to speak about. All the vehicles need some cooling air for either the fuel cells, the batteries, or even the engine. These in and outlet of your internal flow, they're also quite interesting, and I like to speak about how to design these interfaces. A proper design can save a lot, especially by using the momentum added by another heat source. It might be possible to reduce the installation drag close to zero. Let's take a look at the example I put here on the right. So figure A shows a classic passenger car vehicle. It has high drag and the mass flow is quite good, like we see down in the bar plots. Now, when we look at type C, the air flows into the radiator at the lower end and flows out at the upper end again. So normally a little bit more hard to realize on the most vehicle, but we have a really low drag and the mass flow is nearly the same. So I want to just give the conclusion out that inland and exit with phase and normal stream direction does not necessarily include low drag values. Be creative and experiment around to get the optimum design. Beside the inlet, of course, there are the exhausts. Nearly the same importance yields for them. In general, we can say that they should be placed in low pressure regions or low pressure curvent areas to make them even work a little bit better, to perform them better. But attention here, the outlets, they always increase the boundary layer thickness and therefore the likelihood of that phenomenon flow separation, which leads even to more drag. We already had that in the schematic car slide, that flow separation is mostly included with drag. Let's have a look at some examples here as well. For example, in part A or in figure A, here we have a conical sheet metal, and the influence in drag and pressure is quite all right, I would say. In part D, we have a flush exit. But compared now to part A, we have nearly no influence in pressure and less influence in drag. And additional, when we set it right, then we can also improve the momentum transport to the boundary layer and bring more kinetic energy close to vehicle. But be patient with that. Okay, closing up this really nice reality one, we like to switch also to the virtuality, which is also a big part. When it comes to simulation, we should talk about this as well. And why should we use simulation? What are the common methods? Or maybe some questions who are asking yourself. So what and why should we use simulation? First of all, maybe there's a pound of money, of course. Here's more comparison. The small prototype developed in the high-end wind tunnel, it's quite expensive. Another point for student teams, it's a big point as well, that there is no wind tunnel or that you can't use it all the time. So computational fluid dynamics is a flexible and fast alternative to wind tunnel experiments. CFD offers almost unlimited possibility for the analysis of flow fields. You can just click on the mouse, zoom around in these computational domains, and check every value separately. Coupled with this really high computing power of today's computers, CFD makes it possible to develop more complex aerodynamic components and further increase the performance of the vehicle without building and testing everything like some big car companies do when they produce these mock-ups or prototypes. But let's have a look what's on the market. So on the market, there are two big ones. These are just the common ones, I would say. I just picked those. So we have the Navier-Stokes approaches, which are maybe known through fluid dynamic classes, and another one, the Lattice-Boltzmann one. The main difference in them is how they interpret the continuum. The graphic on the right summarizes those differences quite good, I think. So let's start with Navier-Stokes. Navier-Stokes is a conventional CFD solver, and it uses a macro scale interpretation. It means that length scales are as we know them in meters, millimeters, or feet or inches. The continuum is divided in small cubes like your room. The wall is 5 meters long, the other 3, and we can divide this room by having 1 square meter places all over. The Lattice-Boltzmann method, in comparison, is a particle-based method, and it uses mesoscale interpretation. That means that the length scales are in the region of the mean free path length. Maybe known due to quantum mechanics class, it's the path length where 100% chance is given that two particles will collide. And the continuum is now not represented in cubes, it's represented in particles, which stream in these continuums. To just name the last one, it's a microscale simulation one, which cover movements of atoms, but we don't take them into this webinar into account. Both of the methods, like Navier-Stokes and the Lattice-Boltzmann, are often used or implemented with a finite volume approach, which is used to specially discretize the continuum. But now, if we take the comparison from a theoretical view to a practical one, we can show a little bit more advantages. In a direct comparison of the method, of course, both can describe the external aerodynamics. The Lattice-Boltzmann method is transient and explicit. The Navier-Stokes is implicit, mostly steady state. So the Boltzmann, due to its transient and explicit, we gain more accuracy. It's possible to design aerodynamics more exact, especially when it comes to high-end efficiency. It's even possible to look at aeroacoustics. In the Navier-Stokes way, all the transient informations are often averaged and summed up into one single shot or frame, the steady state one. So we can't capture all the effects. Example, the cavities or the vortices around the wheels. When it comes to the mesh comparison, there are also some difference shown in the image below. In the Lattice-Boltzmann, we have a surface mesh, which is really a low surface mesh requirements, which shows that we can see around the edge it doesn't get way finer. In the Navier-Stokes one on the right, we see the high surface mesh requirements. Around the edges, the trias get really slow and they are high quality. It takes a lot of time to work on this. When it comes to the volume mesh, the finite volume method in the Lattice-Boltzmann version is a pure Cartesian grid generated automatically. The Navier-Stokes one, it's locally adapted. We need to refine to its surface and try to form the best match around these complex geometries. Last point, maybe comparing the runtime. For a transient simulation, in LBM, we spend around half a day. In Navier-Stokes, we easily spend 2 days for the same transient case. That means in Lattice-Boltzmann, we have way faster turnaround time, and we can adapt really fast and quickly to design changes or new ideas. Probably you're all asking now, what is this Lattice-Boltzmann method in detail? Let's have a look into some small last theoretical base things and then start off with the practical thing. So, the Lattice-Boltzmann method, it's based on the Boltzmann equation. The Boltzmann equation is similar, or not similar, but comparable to the Navier-Stokes equation, but now in a totally different approach. It's solved on the lattice. The lattice is constructed out of these voxels. On the right, you see one. And now the solving step is separated in 2 steps, the streaming step and the collusion step. Particles stream in determined direction in the streaming step. Then they collide in the colliding step, and in the colliding step, new velocities for the next streaming step get computed. Now we discretize, and we just allow 19 different velocities, because we use a D3Q19 velocity set, 3-dimension, 19 velocities. Due to this discretization, we keep the transient nature of the flow inherently respected, and the physical behavior is determined directly by the viscosity of the fluid. So let's take a small look into the iteration process in detail. The iteration process, like I already said, is divided into the colliding step and the streaming step. Up in the right corner, you see the Boltzmann equation. It sets the recent and the equilibrium density of particles into relation. In the collusion step, of course, we determine the next velocity. In the streaming step, they stream in the direction with the assigned velocity. Based on these equations, we can cover back the macroscopic moments like velocity, density, and pressure, and then reach to our transient simulation result. Now just summing it all up, the theoretical part was maybe quite a deep thing, but let's break it down to some basic things. We have low surface mesh requirements, trivial volume mesh generation, and transient simulation, which should be even more interesting in regard to high efficiency aerodynamics. If you have any questions, please dial into Menti, it was listed below, or we also, beside this, we have an ebook in the end, which will summarize all theory and give more information about it later. So don't hurry, there's still time to get the theory in place. So let's get back to the slides. If we know, it's quite enough with theoretical background. Let's see how the things really work. Every simulation has a simulation pipeline in this general way. First, the preparation. The surface preparation is what we do in Inspire. Then we go over to the pre-processing, the setup of the simulation in with the wind tunnel, following with the solving, where we use ultrafluid X. And the last step, we post-process the results by using AccuField View. Let's have a look in the programs in detail. From design to manufacture, all single easy-to-use platform Inspire offers intuitive and easy-to-learn user interface where we can form the shapes with polygonal modeling, or what I really like, continuous NURBS geometry, where we really control the whole geometry. We have some sketching environment, and of course, we can discretize to surfaces, which leads then to a smooth transition to virtual wind tunnel. Altair's virtual wind tunnel is a vertical application tailored for external aerodynamic studies. It's designed with the users, and it needs in mind the graphical user's interfaces provide easy access to problem definitions. We have an automated and customizable report generation, and we have a good design evaluation. From there, we export then to UltraFluidX. UltraFluidX is the main part. It's a simulation tool for the prediction of aerodynamic properties. Technically based, of course, on that lattice-Boltzmann method. This allows us transient simulation, ultra-fast transient simulation, which leads to small turnaround times and quick design changes. It's optimized for GPUs to deliver extreme performance. When the simulation has determined, we can easily import it into Accu Field View, where we do the post-processing of the simulation, either in the quantitative analysis by generating plots or diagram, or in a visual one, having a vector scene, a scalar animation, or in this case, it is also possible to do renderings with backgrounds and materials, which makes it really look super interesting. But why am I talking that much? Let's have a look in detail how it's really looked like. I prepared a model which is just popping up right now for you guys. We're here in Altair Inspire Studio, and we got the Terraphanic, which was handed in by an EcoShell Marathon theme. Thanks for this, guys. And we like to just see how the program is working. The last days you had already a small introduction with Eric in the Altair programs. The workflow here is quite similar, but I want to just point out a bit. So first of all, up here you have the move thing. I found it really important to know how to move and how to control. When we click here on move, we can either move it up or down. And when we like to rotate, we just click on the mouse wheel, and then we can spin around the center of gravity. When we translate, we just use the right mouse button. And when we select like this, and now we can translate the model around maybe 10 millimeters, or let's put it on 25 exactly. Oh, we got a problem here. It shouldn't be doing it. Yeah, maybe too much workload here. I really be sorry to happen that. Should be working right now, but yeah, let's skip that and continue first of all with the more excited part in virtual wind tunnel, which is the main tool to set up the simulation. I would like to show you that we can really customize easily the tool and use the tool Inspire to optimize or maybe to create a small wing or flap on the top or below, and then smoothly export it to virtual wind tunnel. Virtual wind tunnel is made similarly to Inspire. We can, of course, rotate this vehicle by the same amount with the same controls. We can translate it, and we can select it like this. I just imported the model straight off, and then I stopped to wait for you guys. So let's start with that. First of all, we like to set some good settings up here. I just take the model browser and the property editor. It helps you to keep a good control over all your setup. Then we just speak about the streamlined action user interface. We have system, and we just follow it all up until we run the simulation. You just have to follow all these steps. Now I like to start to create a wind tunnel with you. So we click just on Edit Wind Tunnel, and then we see popping up a wind tunnel directly. When we like to enter the inflow velocity, we just enter what about like maybe 40 kilometers per hour. And due to the SI representation, virtual wind tunnel automatically transfers this to meter per second. If you are in American imperial units, then you also could enter those as well. It's quite handy, I think. So coming back to the dimensions of this one, we can now set easily the width, the length, and the height of the wind tunnel. I will leave it like this for the second. We can deselect the wind tunnel again and continue with the next ribbon popping up here. It says identify parts. I zoom in a little bit for this one. So if we click identify parts, now Ultra needs to know which are maybe parts, maybe the radiator or maybe the wheels would have to be handled separately. When we click on this and click on the part, we now got this car ribbon still here. I think it's the default in this way. So we just gonna unblind or disable the wind tunnel by just clicking it, and it just makes a little better view on the wheels. Then we click on the identify wheel button up here, click on the identify wheel, and then we just select those. When we did this, we changed the icon of the body of this element, changed it to the wheel one. That's really, really helpful to just double check. Now to make sure the wind tunnel is in a good position and the wheels touch the ground, we can select the perspective view and then we can select the orthogonal view. I was already in orthogonal view, I realized, and there you see that we slightly penetrate that wind tunnel wall, so it's quite good to have it like this to maybe simulate a kind of deformed tire there. The tire velocity and rotation rates are easily computed by Altair virtual wind tunnel as well, so we don't have to care about it. Due to the inlet velocity, well, now I'm just getting lost a little. Yeah, good option here to have these keys to just get you back when you're lost in mouse control. Happens to me still, but yeah. So when we virtual wind tunnel just takes this inlet flow velocity and therefore computes the rotational speeds for all the tires. After we set up the tires and all parts are assigned, it's important and a main goal to check the normals of the surface discretized objects. Here they're now displayed in red. I don't have to select any part. Now we could select more parts, but here it's already done. All normals turn outwards. It means that Ultra sees the fluid outwards the geometry. If they would turn inward in blue, Ultra would interpret the inner of this body as fluid domain, which is, yeah, not that suitable, I would say. Okay, we got that done. So we are nearly ready to run the simulation. But now we just have a really coarse mesh in the far field. We can check this by going on mesh controls and element size. Here it's around 20 centimeters. I think it's quite good for the beginning. But now the wall domain would be resolved with these 20 centimeters. So it would be nicer to have maybe a little bit better resolution closer to the body. Therefore, we can use rectangular, offset, or custom refinements. Rectangular refinement would be to just have a part around this. So we just click on the car or maybe a part-based rectangular refinement, and then we click on the object and it generates that one. The part-based refinement are working the same way, and it's quite easy to activate those. There's also a really nice option when you run design studies. You don't have to set up all the mesh controls all the time again. You can easily click on File, Template, Import Full Simulation Setting, and then select the XML document, which is automatically exported by Virtual Wind Tunnel from your first case. Then you click on OK, in German öffnen, and you got all your mesh controls and everything locked in and filed up. And also I have prepared, of course, the body-based mesh control, which I indicated like this with these arrows. And down here now in Property Editor, you can see all the details without clicking it. I like it a lot, but just wanted to point that out. The simulation is nearly set up in total. So quite easy, right? We just need the material. Now we have air selected. Of course, that makes sense. Need some specifications to give here, but I think this is in the default library, but we can also set up some own materials, maybe the airflow from your last wind tunnel session, where you also had a belt system implied. Then you can do an easy validation of your results by using Ultra. When you set all up, you just click on Run, easy. Then on Export, and then you're ready to go with the simulation. Now we could start simulation. To wait for simulation to determine, and probably it would exceed the limit of this webinar by a little bit. Fortunately, I have prepared all the whole thing. We switch back to the slides to have a look at some results. So back on the slides, we now just have a small excursus to just summarize the facts you all heard in this practical session. So first of all, what about the surface requirements? The surface requirements can break them down into only triangle elements. The surface should be just covered with those. No quads, just trias. The element quality is of low importance. Part intersection is allowed, so don't matter about that. And then the most important one, I think, is that the surface normals must point outwards. A good recommended setting is that to have everything closed and watertight when it comes to meshes is quite a usual problem. But if there are small cracks and due to cut problems or something else, it doesn't matter for Ultra that much. So sometimes it's able to even get those things done. And I really liked it because you just save some time by carrying around the problematic places. When it then comes to the setup of the domain, I also have some guidelines for you there. So first of all, it's important to understand that voxel size and number of iteration determine the computational time significantly. In general, a good rule of thumb is to have around 30 to 50 flow passes. These are suitable to reach convergence in automotive setups. One flow pass refers to the time which takes for a single fluid particle to completely stream over the entire body of the car. Then, when we now speak about the coarsest voxel size, often it's common to have what we had 0.2 meters. The smallest one would probably be 0.051. But for me, a good number of twos is 0.992. It's a good number, and you will figure out why when you set up your simulations. Coming back to the domain. The domain should show a blocking ratio of around 0.1%. So I mean the projected area of the vehicle in flow direction divided by the area of the inflow section of the wind tunnel. On the right, you see there are given some dimensions in respect to the vehicle dimension. I thought it makes it easy for you to adapt in your own vehicle. If you have the wind tunnel in these kind of proportions, you easily can set up your own simulation and have a good baseline to start your mesh iteration or as you do your design iteration. Finishing up with the far field from a relative coarse Cartesian background grid, the mesh should consecutively refine towards the surface, like we already discussed in this small presentation. And the outer levels we already saw are therefore often created by boxes, and where I have some guidelines as well for you. Talking about rectangular refinement, it is made from interest to know what they like to achieve. So we like to achieve around 3 to 6 millimeter voxel size at the boundary to the car geometry. Usually it will take about 8 different refinement levels to get down there. So I wrote down these guidelines in the table to give you some variables to iterate. The numbers in the bracket, they are dealing about the length, what should be before the vehicle. The numbers without the bracket are showing the length behind the vehicle, like we had on the last slide. But attention when you set up these refinements and tune around on them. Time stepping on refinement level 0 yields to an adequate subtime stepping in the next refinement zones. Means one time step on refinement level 0 covers 2 time steps on refinement level 1. This is all because it's an oak tree based 2-to-1 refinement techniques. So I just want to make you sensitive for the cost of the refinements. Don't wonder that you end up with way larger cell counts. Now we are close to the surface, and we're getting even closer. We need high refinements, either based on these offsets or the custom volumes. So maybe creating some custom ones. We could, first the offset ones, the part-based ones. Here the whole body shown left shows high stresses. The conclusion out of there, we need part-based refinement on the whole body. Those regions with high stresses are regions where turbulence appear close to the body and where highly transient character of the air is displayed. The picture on the left side shows the transition from the coarse mesh at the top down every refinement level to the really fine mesh, which is a rub then around the body. First we have rectangular shapes, then we have a rub shape. Instead of defining these rubs, we can also use custom-made volumes to have a control about our meshes. These predefined custom refinement zones can be adapted to new similar geometry using a morphing tool in the Spire, what I really love to show you. But it's quite easy to handle, so keep in mind this option. For example, here on the mirror of the Roadster, shown in orange, there's an idea that you can morph a volume around that to control the mesh. Another idea would be, like in the lower animation, around the wheels. The region can be extended to fit the whole tire weight. So you don't need to have an offset, you can just do it manually, then you have less to the front and more to the back where the result is, and in the end you gain more accurate results. Coming already to that point of tires, additional information for you maybe. You have these outstanding wheels on the Shell Eco Marathon vehicles, which may influences should be analyzed more details because it's a big proportion of the vehicle. You could use the Altair solution radials to create deformed tires, like here in these animation. And then you get even more accurate results and you can create your package more efficient. If you have any questions or guidance on setting up the simulation, of course, like I already said, there is an ebook available which covers these guides in detail. As well, this recording gonna be online, so you can jump back into these slides and have a look what you care about and what to look for. Okay, let's close up the lecture part. Let's dive into some cases I prepared. I take all account in these guidelines and run those cases. We have the initial case from Terraphenic from Theo Grass, which was sent in, and my personal creation to have a flat front bumper. I thought maybe it's nice to add a cooling inlet for the battery or fuel cell. Or another good change I had was a lookout or a hatch for the driver to have a better overview of the track. Let's see how they performed. So when we look at the results, we first have to think about the computational time. As I already said, UltraFluid X needs GPUs to run. There are some older K80 graphic cards and some newer V100 graphic cards. I just run a few cases to just give you a feeling how long it takes and what to look out for. On a few older resources, the case run around 12 hours. On the newer one, it's not taking even an hour. And in both cases, Ultra's implementation achieves the same coefficient and the same quality in results. Let's take a look at the quality. Looking at the result and here the progression of forces, we can see a launching up section at the beginning, where the flow gets accelerated from 0 meters velocity to 11 meters per second, at least 40 kilometers per hour. And we have a peak up there in the drag and also in the lift ones. This transition peak is where the air switches from laminar to turbulent flow. You can spot it quite good. Then, when we look on the solution, the drag is nearly constant, it converges against a value, and the lift fluctuates around kind of mean. Conclusion here, that the simulation progress looks quite good and that it's worth to post-process the simulation. Do it every time before you really start to look into all the other things. This is really helpful to just save some time there. So, summing up taking the average of the last iteration, we can point out the CD and CL. The CD differs around 0.023 and the CL about 0.354. So it means both got a little bit more, of course, or wonder. As we see in the animation here in transient kind of thing, in the transient way, we see the wakes at the front hatch determine the downstream flow field quite heavily. Also at the front pumper, we see a way larger pressure zone, and the roof contour overall also disturbed. So maybe it was not that optimal or suitable design what I took here. To confirm, let's have a look at some more quantitative results for especially the sectional drag. The sectional drag and lift these plots are generated by slicing up this vehicle in around 100 sections in this case, or even more, and then computing for every section the drag and the lift coefficient. Now I've just plotted those ones in these plots with the model itself in the background. Now we can see the high influences of the drag at the front bumper can spot it quite easily in the left picture. We have the huge peak in red, which jumps up way higher than the other case. As well, the increase of the lift caused by the hatch or lookout thing up there, which is spotted with the blue really big spike. There's also a drag spike as well. Now another way would be also to look at the cumulated drag and lift values per section to get a really nice understanding in different kinds. To look at the accumulated ones, we see that the values now get summed up of these slices. Now we should look out for strong gradients, indicating major influences happening on the body. Offset in drag at the right beginning at the front bar can spot it quite easily in the custom model. The number will be changed with the red line is totally different. So that means that maybe this change was not the perfectly one. Changes on the roof contour imply huge lift changes. You see the steep gradient just rushing up the scale and leaving the plot up on the top. Yeah, like I already said, maybe the body changes were not suitable, but let's determine first if it really comes from the body. And of course, no surprise, we see when we look at the drag per part, we see that the body has gained some influence. So let's come into lessons learned and see what we really can take out of that design. Maybe the design we already had, that conclusion was not the suitable one. So let's go back to the last design iteration with a flat, with a flat or like a more streamlined front and the lying driver position, which allows more streamlined design. What could be tested for the next iteration would maybe to back tubercles of the Humeback whale on the wheels housing to decrease the drag. We saw on those plots that the drag sometimes is a little bit rough around these wheel housings, and therefore I had the idea to have a look on if we can improve something with that. Of course, there's something you should definitely take home. Learn from the tests you made. Improve and try new concept and design, and use the post-processing techniques I showed. Do not only trust in nice and colorful pictures like these animations. The quantitative results are saying way more. Okay, and what about the tools? Is there any lessons learned? Of course there is. So when we just summarize it all together, the preparation time for the surface mesh and the automated volume meshing and the opportunity to perform transient aerodynamic simulation, this is a big advantage. Also, the quick design changes and simple workflow with this nice intuitive streamlined GUI, they allow fast turnaround designs, and so you are able to adapt to all trends. Just easily test out this humbug whale idea. Maybe it's worth to try and have an implementation on the next vehicle. Summarized, I just want to say they are easy to use and save a lot of time. And I know from my student days that sometimes time is the most valuable good in the project management to get the car ready in time for the next big event. What we hopefully going to have next year. So now the big question left is how to get started. Let's round up this session to have a look what you can do and how you can prepare to start your own simulation. As already announced, we published a book which summarizes all content you heard in the last hour. Download it. It gives theoretical and practical advices and guides you through the first steps. Just sign up at Altair University and apply for that ebook list up there. Then as well, sign up for the Altair Student Edition or for a sponsorship. Now you're of course asking probably that how we can get resources to compute on GPUs. So get in contact with Altair University. I just wrote the email down here, altairuniversity@altair.com. We are working on getting a benchmark CPU to run several test cases. And of course, reach out to the original Altair team to develop the new path. Maybe there are also some universities which are right now setting up GPUs. So contact your professors and check out the situation. It might be possible that you already have hardware to compute. So why don't you check it out? Before the last end, I like to thank out to the Shell Echo Marathon teams from TU Grad and Duke University for sending in their nice racer geometries and make it really possible to show these hands-on cases. Thank you all for tuning in today. And yeah, it was a pleasure for me to have you guys all here with me for that hour. And now back to Norman in the Shell studio. Thanks.
Thanks, Paul, so much for your very illustrative and very hands-on presentation. So I think a really, really good overview about aerodynamics and what to be considered in Shell Eco Marathon. For everybody on the line, I hope you have posted lots of questions in the meantime. Don't forget, please go to menti.com and enter the passcode on the screen to post your questions or simply type it into the YouTube comment box. I look forward to receiving really, really tough questions for Paul, and I'll be really happy to pass them on. So your chance now to ask about aerodynamics, whatever you wanted to know. And Paul, just to get you warmed up a little, here's a starting question. Somebody is wondering, for designing a car, is it necessary to be good in sketching or drawing? Or can we directly draw in this software?
There are some options in Inspire Studio which makes it able to create some parts and modify it. But in general, Inspire Studio is not a typical CAD construction software. We like to have a round and alternative, maybe a suitable and general source where you can modify, interact with parts, do renderings, and basic, like not basic things, but more extended things. Basic things like in CAD software, where you just have measurements and this, are not possible. When it comes to CFD, of course, you should have a kind of idea what you are looking for. But then, of course, there should be someone in the team where you could ask to create some more things, or some other students when you're not good at that. But I think there are also options where you can easily create one spline, and we have that done. You can modify even more and more, that you don't really have to create sketches on your own.
Mm-hmm. Thank you very much. And somebody else also interested in using Ultrafluid X, asking Paul, how can I get going with Ultrafluid X for my vehicle? Any top tips?
Can you say that again? There was a kind of buffer problem we had here in Hamburg.
No problem. No problem. So somebody is wondering, can you give some top tips how I can get going with Ultrafluid X for my vehicle? How do I start?
Yeah, of course. Maybe we can just switch back to our slide 50 in that case, to really point out again what you should do, guys, to really get started off. As I said, there is the ebook available. The ebook is dealing about the theory and also the guides and lines which are needed to set up a simulation. It's a nice storytelling thing where you have a former student team, which is then, which are first introduced to Ultrafluid X, and I tried to set up their own vehicle there. So you have all the basic steps right down there. The second is you need GPUs, and then I think it's not the long path you need to take. Download the Altair products and install Water Wind Tunnel. You have the hardware, load up in the model, and then start to design the first setup. You can use the guidelines we showed, and also you can customize them a little. And then you run it, and then you already got your first Ultrafluid X simulation done. Quite easy, eh?
That's great. Yeah, even I got that, Paul. Thank you.
Good.
And now a question, obviously, from a practitioner who's already been working with the software. Is it important to include the movement of the ground into the aerodynamic analysis?
Yeah, really, really nice question to speak about this. It depends always on the case you are looking at. So if you're driving on the road, of course the ground moves towards you or in respective to you. But when you're now in the wind tunnel where the ground is fixed and you don't have these nice belts like many universities can't afford or don't have at all, then it might be nice to have a steady ground that you can really validate your wind tunnel results by using Ultra. So that you don't need that ground. Of course, a moving ground is creating additional effects like the Venturi effect. It even accelerates the air, what we have in the schematic picture we had. It even accelerates the air under the other body and also changes the drag and lift value sourcing from there. I think it should be just discussed in the special case you have.
Okay, thank you very much. Also, another question, and again, is maybe a the answer again. I'll be curious to hear. But what is more important to get better lap time, to reduce the drag or to reduce the uplift?
Especially in eco and shell eco marathon, I would say it's all about the efficiency. So if your vehicle drives quite nice, so if you can sit in the car as a driver and you are confident that the vehicle doesn't roll over, doesn't slip in the corners, that the torque from the tires has a good transition to the ground, then I would say the lift has a quite good value. But the drag always should be lower or lowest possible, because drag like we had in the beginning, is directly related to fuel consumption, either petrol fuel, battery fuel, or fuel cells. So if you spend more drag, you get less range. If you have a better optimized aerodynamic, you can drive way farther.
Okay, that's very clear. Thank you. Also here about the usage of the tool. Somebody is asking, when does it make sense to start applying CFD analysis? Should you do it when you have only rough data of the body shape, or more later when you have a defined body?
Oh, that's a good question. Like last days or last years, when I was in Formula student, I always had asked myself nearly the same. Um, Sometimes it's even hard in the design progress to adapt to all design changes the team made, and you're just rushing in that case with your aerodynamic setup. Like we had one setup here from the Terrafanic, and it was like you saw quite simple. So you have a rough body, and you had some disc which were modeling the tires. So there might be the question, or we should maybe postpone the question to that point: how important is to have a detailed car? Is it maybe possible for you to generate your car or to abstract your car geometry by using simple shapes? That's already quite a good approach to get started. So if you have a buggy, maybe just take a cube and 4 or 5 discs and look out that the dimensions fit in the first place. And then when your team iterates to a more finished design, then you could adapt there again. But only, of course, if you need CFD in the first place. First, of course, you should have all the other components ready. When the car is running and you like to gain for efficiency, then I think a CFD is a good tool to choose and to take an account here.
Okay. We had another question here saying, I would like to use the air tunnel. Where can I download this tool?
Okay, like we already had, you should sign up for Altair Student Edition or even apply for a sponsorship. The Altair sponsorship, they include the virtual wind tunnel and as well Ultrafluid X. And those can be downloaded on Altair Connect. I would say when you then log in with your account, you get your sponsorship. Then you easily install it and then it's ready to rumble.
And I suppose in order to apply for your special Shell Eco Marathon sponsorship from Altair, you go to the Altair University website and fill out the form.
Yeah, of course. It can be found on the altairuniversity.com, like you said, Norman. And there is a student option. And then when you click on there, you go on student competition and then request sponsorship. Maybe it's possible to just have a look at this one. I just open up Google Chrome in this time, and then we can have a look directly into this and make sure you all find it. So if you type in www and then Altair University, I already got it there. Oh, lovely. But we just take the main one. And then up here, we go on student. And then we can roll down to student competition right here. So just went on Altair University, clicked on student. Now we're rolling down to student competition. And now a new tab pops up. And here we can find request sponsorship right here, the blue one. So and when you click on there and you fill out the form, then the original team will get in contact with you and figure out the next steps.
Yeah, thanks. That's very clear and simple enough. Another question that has come in, and again, I would like to remind you that's your chance. We still have a bit of time for Q&A. Keep your questions coming either on menti.com or the comment box on YouTube, and ask Paul any questions about his presentations that you would like. Please menti.com or the YouTube comment box. Another question that we had come in was, how can we, sorry, I lost my screen. I need to find the right one. Here we go. For LBM, you used a voxel mesh. What do you do at the vehicle surface, since you will not have the body fitted volume mesh anymore using the voxel approach?
Yeah, maybe we can therefore have a look on a slide. I think it should be open up right now. The slide 36, which gives us a more detailed look into the volume mesh. And now you can think about again that we have way up in the back, like in the coarse regions, we have this rectangular shapes, and then we get closer and closer to the surface. On the surface itself, we have then a fine mesh, and this is has a translation into a wall model. The wall model is basically in charge to generate the boundary layer interactions and also the boundary particle interactions on that place. And this high quality wall model is like the main source or the main thing which is important for these boundary layer accuracy.
Okay, thank you very much. We maybe looking back at the website, we had another question coming into the previous one. Are there any video tutorials available for the software on the Altair?
I think we can answer this without looking at the website again, because the content I showed you today, this pipeline is nearly brand new and is just coming from the software developing stage and testing, and that's the reason why we are still working on some webinars there, or maybe some material, but at the moment there is none. So this
something to look out for the future.
That means for the future that maybe there are coming some. We can't say that right now. At the moment, what will be there is this recording on YouTube, where you easily can pause the things. And also, I have to refer back to the ebook again, which is really intuitive and covers everything you need to know.
And of course, why would anyone want to watch a video tutorial if he can watch the recording, he or she can watch the recording of your presentation here today? Absolutely. Another question that has come in, more on the software side, wanting to understand a bit more, what turbulent model is being used by the solver?
Yeah, that's a good point. I think you got me on this one. I kind of lost in the right description there. Okay, maybe you just contact us on the Altair University at altair.com, and we figure out to give you a value and quality answer on this one, that we can make sure that you understood it in detail. If you like, there's also an opportunity. If you look in the internet, there's an Ultrafluid X guide available, where you can download on the same page where you can download the Altair software. In this guide, all the details regarding Ultra are listed, and also all the settings on all this are explained. So beside with the wind tunnel, there's also a manual or guide coming with the software, which is even giving you more details and information.
That's clear. Another question, can I do thermal simulation with this tool as well, or only aerodynamics?
Oh, that's a good one. someone who's doing both at one time. That's nice to hear. So the thing is, Ultra is only for external aerodynamics. It's not capable of to do thermal simulation. On thermal simulation, I would prefer to use AccuSolve. AccuSolve is also an Altair solution, which is then capable to show you some or to even solve thermal problems.
Okay. And here's one for the practitioner who wants to know the outcome before doing the modeling, but maybe you have a guiding figure. How much drag reduction can I expect when removing the two side mirrors?
Okay, well, that's quite detailed, no? But let's think about by removing the side mirrors, which are really a high drag source especially when it comes to passenger vehicles. I think you can save around 5 to 10 counts, what we say in aerodynamic language or CFD language. That means counts means thousands, so 1/1000. So when I speak about 10 counts, I mean 10/1000 of the overall drag.
Okay, that
Something
can
like
make the
that.
difference between winning and losing, so worth considering. But of course, check your rules if that is allowed to remove the mirrors, or maybe you have to put them in a clever place, like maybe inside the body and get the angles right. What approaches are available in Ultrafluid X to model rotating wheels?
Okay. Yeah. Nice and detailed as well here. So we used in this small presentation, we used the normal rotating wall approach. When you then also define a volume around that rotating wheel, and then you are able to also use the multi-reference frame approach, which is a little bit more detailed and which covers the interaction between not only the boundary and the particles to the boundary side, also all the particles which are then in this specified domain. So this means all the particles maybe in the rim where we usually use it, there we also then have interference between the rotation and the outer flow, like we discussed in the beginning where I showed the wheels, that we have these complex flow phenomena happening there.
Okay, thank you. So last reminder, everybody, we have a couple of questions left for Paul. If you have any other questions, this is your chance, last chance to get them in, send them through to menti.com or in the comment box on YouTube. So your last chance to put a question in, or we're having a couple more here. Next question, Paul, is can we use the aero loads as a boundary condition for a structural analysis?
Yes, yes, it's possible, but the option is still under progress. That we work on that to use the aero loads as a mapping onto some FE models. Yeah.
Okay, so again, watch out, might be coming in future. And the question here is downforce important for race cars? If so, why does why shall eco marathon cars not focus on downforce body design, but less drag only?
I wouldn't say that they focus only on drag, but I would say when the overall driving is good and you feel comfy in the car, then the drag should be attacked first. Lift is the main value which is determining the driving or like say the cornering behaviors. So if you have problems by taking a corner that sharply or even driving fast around like small edges or yeah, I don't know, then you should look out for some more lift.
Okay, good. Well, that answers all the questions, Paul, that have been asked here today. I'd really like to say thank you once more time to you and the whole team from Altair for your time and for the very interesting and helpful presentation. And equally, thanks again to all our participants tuning in today and taking part. There are more virtual sessions coming up later in May. So if you haven't registered yet on the website, please go there. We would love to have you join the other presentations. But until then, I say thank you and have a great day. Thank you.
Thanks, guys. Bye bye. Thanks.